Hi everyone. In this video, we will begin our discussion of series of functions. While we have been looking at sequences of functions over the past several videos, we haven't looked specifically at what happens in the case of series. Now, as we saw with sequences and series of real numbers, the proper way to really consider a series of real numbers is to think of the associated sequence of partial sums, and exactly the same is true for sequences and series of functions. We'll think of a series of functions in terms of its sequence of partial sums. So, with that in mind, we've already seen many of the results that we will need in order to analyze series of functions if we simply wish to think about them as sequences of partial sums of functions. However, we'll spend the last two videos looking specifically at series of functions, interpreting some of our earlier results into the language of series, and looking at specific results that relate to series of functions, particularly special types of series, such as power series and Taylor series. So to begin, we first want to look at an important theorem in studying series of functions, a theorem called the Weierstrass M-test. So the test says let f sub n be a sequence of functions, and let m sub n be a sequence of constants or sequence of real numbers, such that each of the f sub n functions is bounded, its absolute value is bounded by m sub n for all x in the set D, where D is the common domain of the functions f sub n, and for each natural number n. If the series m sub n converges, then the series f sub n converges uniformly and absolutely on the common domain D. So before we discuss how we might go about proving something like this, let's first just think about this in terms of an example. So consider the series sum n equals 1 to infinity of cosine nx divided by n squared. Okay. So this is a series of functions, right? And certainly, I could try to analyze this from a pointwise convergence point of view. So I could say, let's fix an x. For a fixed x, this is now a series of real numbers. And then I could ask myself, does that series converge? But even then, actually, this would be a little tricky even for a fixed x. It's not clear, for example, this is not an alternating series necessarily. So it's not exactly clear what tests we might use. But we want to actually look at this in terms of this Weierstrass M test. So the first thing the Weierstrass M test says is, okay, to each of these functions, so I'm going to think of these as the f sub n's, I want to associate an upper bound, which is capital M sub n. So if I look at these in absolute values, these f sub n of x's, these absolute value of cosine nx divided by n squared. Okay. And if I look at this, I can bound the top. Cosine of nx in absolute values is always less than or equal to 1. And I'll leave the bottom as n squared. And so this will be my m sub n. So again, what we're saying is I want to create these m sub n's by bounding the absolute value of f sub n of x, but this bound m sub n needs to work for every x in the common domain D. Okay, so notice that this bound works for every x value, right? And now I can find one of these m sub n's for each natural number n, right? I can do this for each of my functions m. So, in particular, if I wanted, I could list these out, right? So the f sub 1 of x, right, is less than 1 over 1 squared. F sub 2 of x, is less than or equal to. F sub 2 of x is less than or equal to 1 over 2 squared, which would be 1 over 4, right? So for each n, right, I get one of these bounds, and this is m1, this is m2, so on and so on. Okay. So what the Weierstrass M test says is, well, look at the series of M sub n. So what can I say about the sum n equals 1 to infinity of 1 over n squared? Well, this converges, right? This converges because this is a p series, right? So this exponent is strictly greater than 1, so this converges. And so what the Weierstrass M test says is, well, since this series converges and each of these were a uniform upper bound on an f sub n, then this implies, and this is what the Weierstrass M test says, so this implies that the sum n equals 1 to infinity of cosine nx divided by n squared converges uniformly and absolutely. So again, let's just recall here, right? This is a pretty strong result because it's giving me not just convergence, not just point-wise convergence. It's giving me uniform convergence, and it's giving me absolute convergence, which means even if I were to slap absolute values on here, so the fact that this converges absolutely, right, is telling me that this also converges. Right? So I'm getting more than just regular old pointwise convergence. I'm getting uniform convergence and I'm getting absolute convergence. So it's a very strong result here. Okay. Now let's look at the proof of this. I'm not going to maybe write out sort of the full details of the proof here, but at least we'll sort of sketch out the idea so you get some sense of why this works. So again, the nice thing about this is it allows us, this theorem allows us to convert a question about convergence of a series of functions into a question about convergence of a series of real numbers. And for a series of real numbers, we have many tools at our disposal. Okay. And in fact, the one that I want to use here is actually one we haven't used maybe in a little while. It's the Cauchy criteria for convergence. Okay. So we'll just call this sort of a sketch of the proof. Okay. So let's assume that our f sub n's and our m sub n's satisfy all these conditions in the first sentence. And then we'll further assume that this series m sub n converges. Okay, so the idea is that since this series converges, that implies, the Cauchy criteria implies that this is also Cauchy. Okay. Well, what does it mean for this series to be Cauchy, right? It means that if I look at the difference between the nth partial sum and the mth partial sum, I can make that difference as small as I would like. Okay. So since, well, so then if this is Cauchy, this implies that I can make this difference as small as I would like, right? So what I'm doing here is this is really like the nth partial sum minus the nth partial sum. Okay. And again, formally, it means I can find a capital N such that for all little n and little m greater than that capital N, this holds, right? And I can do that for any epsilon. Okay. All right. So then what I note is that if I let, say, a sub n of x be, or sorry, let me call it a sub k of x, be the sum n equals 1 to k of f sub n of x. So I'm just defining the kth partial sum of this. Then if I look at, say, a sub k minus a sub m in absolute values, sorry, those should be of x. Well, I get by definition, this is the sum n equals m plus 1 up to k in absolute values of f sub n of x. And I can apply triangle inequality here. So this will be the sum n equals m plus 1 up to k of f sub n of x. But these, by assumption, are less than or equal to m sub n, less than or equal to the sum n equals m plus 1 up to k of the m sub n's. And if I look at this, up here, I have that the absolute value of all these things of the sum was less than epsilon. And in fact, I know each of the m sub n's is greater than or equal to 0, right? Because it's bounding an absolute value. So I could actually just drop these off. This sum will actually be positive. And so this must be less than epsilon. And so what we have here is we now have essentially that, sorry, we have shown here essentially that the sum, the series of the fn's is Cauchy for all x in D, which gives us that this converges. Now, how do I know that that convergence is uniform? Well, essentially, I know that convergence is uniform because over here, this choice of capital N that I would need to guarantee this, I chose it up here without any regard to a particular x. So this capital N is going to be independent of any of the x values here. Therefore, this converges uniformly. Okay. Now, how do I get the absolute convergence? Well, if you come right here, you essentially see if I slapped absolute values on these things, I would still end up back in the same place. So the proof would work just as well if I looked at the absolute values of each of these fn's. So I get convergence that's both uniform and absolute. Okay. Again, writing out the details here, it's a nice exercise, how am I going to carefully write out what each of these definitions means, how I'm going to do this. But this has hopefully presented you with a sketch sort of overview of how the argument goes. Now, again, as I mentioned, this is a very helpful theorem when we want to prove things about series of functions. Again, because it converts the question about a series of functions back into some question about a series of real numbers, where those real numbers, of course, have to be related in some certain way to the series of functions. Now, we could just look at lots of examples of series of functions, but there are a few particular types of series of functions that are very widely used. So the first that you often first encounter in a Calculus 2 course are so-called Taylor series. Right? Taylor series are one way of using information about derivatives of various orders of a function at a point to create a series approximation of that function in some neighborhood of that point. So Taylor series are very commonly encountered. Taylor series are a subset of power series, which again are an important family. There are other families of functions. So for example, uh, Fourier series are very widely used in lots of applications in physics. They're also used quite a bit in differential equations. Um, so there are many types of other series, but really, I would say the two largest that you commonly see are power series, and more specifically Taylor series, and Fourier series. We're not going to spend much, really any time. We may have time for a short example of some Fourier series stuff, but we mostly want to focus on power series and Taylor series. So let's begin by just reviewing, what a power series is. So a power series, we can think of this as a function of this particular form. F of x is equal to a sum k equals 0 to infinity, a sub k times x to the k, where this a sub k, these are just presumed to be a sequence of real numbers, right? So the idea is the first term, right, would be a sub 0 times x to the 0, but x to the 0 would just be 1, right? So if I just were to expand this out a bit, right, I get an a0 plus an a1 x to the first plus an a2 x squared, so on and so on and so on. Okay. So in a way, excuse me, these power series are like an infinite extension of polynomials, right? What would happen if I added on more and more and more terms to my polynomial until eventually I had an infinite number of terms? However, they are not polynomials, right? Polynomials have a degree, right? There's a highest power, right? Power series do not necessarily um, have a highest degree, right? You can keep infinitely adding these on. Now, alternatively, we could express our power series as being centered at some particular point, x is equal to a. In that case, we just replace the x with an x minus a. So you can think of this as being a power series centered at 0. This is a power series centered at a. And now that you have some function, right, a natural question to ask is, what is the domain of that function? Well, what does domain mean? It's the set of all x values, right, for which this expression is defined. So if I look at this in a way, this is like asking, what are the x values for which this series will converge? Okay. So one of the first questions we're going to need to answer before we can do anything else is to understand exactly when these power series converge and or diverge, right? That will help us understand what the domain of this function is. Once we have that, we can start to talk about things like, are these functions continuous? Are they differentiable? Are they integrable? How might we differentiate or integrate them, right? But until we can understand what the domain is, we really have no hope of answering any of those questions. So what we're going to want to do is we're going to want to define the set of x values for which this series of functions, this power series, converges. So we're going to define this value capital R, which will be between 0 and positive infinity, and could possibly be 0 or positive infinity, such that f converges for all x in the interval a minus r to a plus r. Now, already you can see some assumptions built in here. I mean, why do I know, for example, that this is going to converge on some interval? There's no reason to suspect that. How do I know it's going to converge on an interval? That interval will be centered at the same place the power series is centered, right? How do I know that? Um, right? And you know, like, so how do I know that any of this is going to happen? We're going to have to prove that. But we're going to find this value r, which we're going to call the radius of convergence. Now notice, because the way we've structured this, the radius of convergence basically tells you as long as you're within this radius from the value a, where your series is centered, then your series is definitely going to converge. Okay. So once you have that radius of convergence, you can then talk about the interval of convergence, right? That's just the whole interval. These are all the x values where it converges. Now, we know it will converge on this open interval. It may or may not converge at its endpoints, right? That is a little less certain. So just as an example here, so you can think about the following power series. Okay. So here my a sub n is 1 over n times x to the n. This is centered at 0. So notice I could just start plugging in x values. So for example, if I were to come here and say plug in x is equal to 1, this would give me the series sum n equals 1 to infinity, 1 over n. That's a p series, and that diverges. And that's just the harmonic series. If I were to plug in, say, -1, I would get some n equals 1 to infinity. See, I'd get a -1 to the n over n. This is the alternating harmonic series. By the alternating series test, this converges. Okay. And now I could plug in other x values, right? Now, for almost any other x value, I'm going to be able to determine whether this converges or diverges using the ratio test. So I'll just sort of give away, if you plug in x is equal to 2, so you get sum n equals 1 to infinity of 2 to the n over n. This is going to diverge. In fact, you can see this diverges. The limit of these terms is not 0. So that will diverge. If you were to plug in x is equal to 1/2, though, you would get sum n equals 1 to infinity of 1 over n times 2 to the n, which converges. Now, keeping in mind that we expect sort of an interval of convergence, and it may or may not converge at the endpoints, you start to get the sense that it looks like this converges at -1, but not at 1, and I'm centered at 0. So that really only leaves me with the possibility that my interval of convergence is this. So if I'm going to have some interval centered at 0, so that it definitely converges all the way down to -r and up to +r, right? So my a is 0, so it's going to go from -r to +r for sure. And then the endpoints could go either way. This is pretty much what I'm left with, what has to happen. Okay. All right, but again, how do I know this has the structure? Like, how do I know it has all this structure? These are all things that we need to answer, and that's what we want to really spend the rest of the video doing, is digging into a theorem that reveals to us exactly the structure of the domain of power series, essentially, right? And how these power series converge, right? So once we figure out they converge, say, pointwise, do they converge uniformly? Do they converge absolutely? Like, how does all that work? All right. So theorem 2.71 from the book will answer that question for us. So let capital R be the radius of convergence of the power series. F of x is equal to sum n equals 0 to infinity of a sub n x to the n. And we're just going to deal with the case where the radius of convergence is strictly between 0 and infinity. Then the power series f of x will converge absolutely on this set, right? So if you look at this, this is the same as saying x is in minus r to r. Okay, so we'll get not just convergence on the interval of convergence, we'll get absolute convergence. We will get uniform convergence if we look on any closed subinterval, essentially, within that larger interval of convergence. So the idea here is you'll get, so here we're doing this all centered at 0. You could do a similar thing centered at a, but between here and here, you get absolute convergence. If you pick any little r that's smaller than capital R, then on this pink closed set, you'll get uniform convergence. And then the last thing says outside of these, you get divergence. So essentially what this does is it pretty clearly lays out the entire convergence picture except what happens exactly at R. So at R, who knows? Okay. And the answer is essentially that's a series by series kind of determination. But within this interval, minus R to R, you get absolute convergence. On any closed subinterval, right, you're going to get actually uniform convergence. Outside of minus R to R, right, open intervals on the outside, you're definitely going to get divergence. And exactly at the endpoints, well, that depends. All right. So what we want to spend the rest of this video doing then is proving this theorem. All right. So we're actually mostly going to just spend time proving the second part. And once we prove the second part, well, we're going to sort of set up some preliminary stuff. A lot of work will go into proving the second part, and then we'll be able to just sort of point at some other things and say, oh yeah, 1 follows and 3 follows. Okay. All right. So to set this up, so suppose that your series suppose f of x converges for some x naught in R. And okay, if I plug in x is equal to 0, it's always going to converge for x is equal to 0. That's not particularly interesting. So let's suppose we get convergence for some x naught that's not 0. Then what happens? Then there exists, well, if it converges when I plug in x naught, then with x naught plugged in, each of these terms must be going to 0, right? If the limit of my terms in my series doesn't go to 0, the series can't converge. Since I'm assuming the series converges for x naught, then the terms must go to 0. And since they go to 0, they must be bounded. Okay, so there exists m greater than or equal to 0 such that a sub n x sub 0 to the n is less than or equal to that m for all natural numbers, right? Again, these terms are going to 0 because I know this series converges when I plug in x naught, and so they must at least be bounded. Okay. Well, then if I take an x that in absolute value is less than the absolute value of x naught, so another way to think about that is you have 0, let's say you have an x naught, and now you're using this x naught to sort of define a distance away from 0 that you can go. So over here would be minus x naught. And if you pick an x anywhere in here, what we're going to do is we're going to show that the series must also converge for that x value. So as soon as you know what we are first sort of showing is as soon as you know you converge at x naught, you know you converge at every x value that's as close to 0 as x naught is. Okay. So if x in absolute values is less than the absolute value of x naught, then if I look at a sub n x to the n, well, I can do a little algebraic manipulation here. Okay. Notice really all I've done is I've multiplied in here by an x sub 0 to the n in the numerator and denominator. So these really are equal to each other. If I started here, I raise each to the nth power, I'd cancel out the x sub zeros to the n, and I'd get back to this. Okay, but the important thing in rewriting it this way is I know this is less than or equal to capital M. Okay, and this, whatever it is, I'm going to call it R. This quantity, since I'm assuming the absolute value of x is less than the absolute value of x0, this is strictly less than 1. So this R, which is absolute value of x over x0, is strictly less than 1. Okay. So by comparison, if I look at this series, right, that series converges. It's just a geometric series. M is some constant. R is a constant that's strictly less than 1 raised to the n. Okay. And so this converges. And by the comparison theorem, the terms in this series are strictly smaller than this. So, and by comparison, we get the sum of these. This also converges. And so what is that telling me? That's telling me that this converges absolutely for all x less than that fixed x naught. Okay. So what this is telling me is as soon as I know that I have convergence for some value distinct from 0, then I have a whole interval's worth, right? And that interval is just defined as all the points that are at least as close to 0 as x naught. All right, great. So now how can we use that to our advantage? Now notice this isn't quite what we wanted here. We've got not that it converges absolutely. We've got to define really what this radius of convergence is. Well, we said before, we really want the radius of convergence to be the largest value for which this works. So it's sort of like finding the largest x naught where this works. Okay, and so that's precisely what we're going to do. Okay, so now let's take and define this capital R to be the supremum of the set of all x greater than or equal to 0, such that this series converges. So the idea is basically look at all the x values where this thing converges, pick the largest one, okay? And then, well, the largest in absolute value, okay? That's going to tell me my radius of convergence. Now, let me be a little careful. I'm saying pick the supremum of this set, right? So at R, it may not converge, but this is the least upper bound of the set of all x values for which this converges. Now, if R is equal to 0, okay, let's just think about what would that mean? That would mean the only thing in here is 0. And that just means that your series only converges for x is equal to 0. If R is positive, okay, which is sort of, again, our assumption here, okay, so if R is greater than 0, or since R is greater than 0 in this case, then that series f of x converges absolutely for all x with absolute value less than R. Okay. And again, that's just coming from the definition, because this would mean that it converges for some x naught as close as I would like to R. And essentially, I can make the argument that it must work for every x that's strictly less than R. Okay. All right. Again, if R happened to be equal to infinity, that would just mean what? It would mean it converges for every x value. Okay. We would just say the radius of convergence is infinite. All right. So essentially here, this gives us the converges absolutely for x is less than R. Okay. Now, it's worth sort of noting, this also gives us that it diverges for the absolute value of x is greater than R. Because if it didn't diverge for all x greater than R, let's say that would mean there's what? There's some x whose absolute value is greater than R for which this converges. But then because it has to converge on everything less than that, right, then all of a sudden that would contradict my definition of R as the supremum of the set of all x values where this converges. Okay, so actually your definition of R here actually gives you 1 and 3. Now it's just a little more work to get to. All right, so let's switch colors here since we're switching to that. All right, so now let's choose. So let's take our R between our little r between 0 and capital R. Okay. And suppose the absolute value of x is less than or equal to R. Okay, so we're getting in the setup here. We want to show that in this case, our series of functions converges uniformly. Okay. Now I need to choose another thing. So I'm going to call this, say, lowercase sigma. So I'm going to choose a sigma greater than 0 such that sigma is between little r and capital R. Okay. Let's see. Well, then what can I say with respect to sigma? If I look at the sum absolute value a sub n sigma to the n in absolute values, this converges. Why? Sigma is strictly less than R. So this is going to converge absolutely. Okay. So this converges. And so similar to the argument we made before, we know that a sub n times sigma to the n, this has to be bounded above by capital M. Okay. So therefore, if I look at a sub n x to the n, okay, I'm going to play a very similar game as before. This is equal to, not less than or equal to. This is equal to a sub n sigma to the n times x over sigma to the n. So same algebraic trick as before here. I'm just multiplying in the numerator and denominator by sigma to the n. Okay. But I'm assuming here that my x is less than R. So this is, or less than or equal to, the absolute value of x is less than or equal to R. So this would be less than or equal to a sub n sigma to the n R over sigma to the n. And now this first term is bounded by M. And this thing, which I'll call, say, well, I guess I shouldn't use R here. I'll call this Z to the n. Z is just what I'm calling the absolute value of R over sigma, which is strictly less than 1, right? Because R is strictly smaller than sigma. Okay. So this series, the series of these terms converges. So this series must also converge. But here, right, we're using the Weierstrass M test, right? So this is our bound, right? The absolute value of each of the terms is bounded by this. This series converges. So this converges uniformly and absolutely. Okay. So now we're a little close to the bottom here. So by the M test, the sum a sub n x to the n converges uniformly and absolutely. Right? And it converges uniformly and absolutely on this interval, right, where the absolute value of x is less than or equal to r. Okay. Now, you have to be a little bit careful about this. You cannot extend the uniform convergence to say this entire interval. The problem is that these, if you sort of come back over here, some of these things are going to end up being one if you don't stay strictly away. So here it really is important that you're able to have this r that is little r that's strictly less than r, so that I can pick this sigma that is strictly between little r and capital R. So you really need that separation. And so you only get uniform convergence on a closed subset of the interval of convergence. Okay. So what we have seen in this theorem really, again, is it's a definition of the domain of this power series, right? But it also tells us a little bit more about sort of how this power series can behave. So for example, if you look at this, just taking the fact now that I know that I have uniform convergence, at least on some set, each of these, if I think of these as a sequence of partial sums, right? Each element of that sequence of partial sums is a polynomial, so it's continuous. So I have continuous functions that are converging uniformly, at least on this set, and so their limit, at least on this set, must be a continuous function. Okay, so what we're going to see next time is that we can actually start to say more about these particular power series in large part because each of the partial sums is itself a polynomial, which has lots of nice properties: continuity, differentiability, integrability. And using some of these properties of absolute and uniform convergence, at least on certain intervals, we'll be able to extend that to say things about the continuity, differentiability, and integrability of power series. In particular, we'll be looking at how those apply to Taylor series.